So in Chem 1A, we learned about the Arrhenius definition of an acid, and there was another one. Bronsted-Lowry, thank you. Like a B something. Bronsted-Lowry. We learned about Bronsted-Lowry and Arrhenius definitions. Here's another definition, the Lewis definition. So here we're focusing on transfer of an electron pair instead of transfer of a hydrogen ion. And if you think about it, a hydrogen ion being a proton and an electron pair, they're kind of opposites of each other, right? So an acid is an electron pair acceptor. It's a hydrogen ion or proton donor, right? It's the opposite. The base is the electron pair acceptor. In the Arrhenius definition, it's going to accept the hydrogen ion. Right? So this expands the definition of acids and bases. And this idea is important in organic chemistry because there are acid-base reactions that we would not recognize as acid-base reactions. So here's a familiar base, ammonia, right? Ammonia accepts the hydrogen ion to form ammonium. How does it do that? The nitrogen has a lone pair. The lone pair makes a coordinate covalent bond with hydrogen who has no electrons. You need the 2 electrons for a bond. So hydrogen basically just gets to ride along for free here. So it's accepting the hydrogen, but it's donating electrons to the hydrogen to make the bond. Does that make sense? So Lewis acids don't have to have hydrogen in them. Here, BF3 is acting as the Lewis acid, and ammonia is acting as the Lewis base. We would not expect BF3 to be an acid because it doesn't have any hydrogens, right? It doesn't work for the other definitions. But the nitrogen has this lone pair, and BF3 has an empty orbital. It's one of those exceptions to the octet rule. We look at its Lewis structure. The boron does not have an octet, but it has the potential for electrons to be there. Nitrogen has this pair of electrons. Boron has a place those electrons could be. And so the base donates electrons to the acid. And now they are together, and that's called an adduct. It's a little different than having a conjugate acid and conjugate base, right? Because we don't form 2 things. We form one thing. So a Lewis acid has an empty orbital, or can rearrange its electrons to create an empty orbital that can accept the electron pair. So molecules that have incomplete octets have an empty orbital that can accept the electron pair. So here we have aluminum chloride and ammonia. Aluminum here has an empty orbital. So it can accept these electrons and form this adduct. Here we've got boron trichloride and diethyl ether. The boron has an empty orbital. The oxygen here in the middle has 2 lone pairs of electrons. It can donate a pair of electrons to the boron. The boron accepts the electrons. So the boron is acting as the acid, and the ether is acting as the base. And again, we end up with one product, because when those electrons are donated and accepted, they form a covalent bond. Don't ask me what the name of that is. Some molecules will actually rearrange their electrons. And this is the sort of thing that you'll see a lot of in OChem. So here we have carbon dioxide, the Lewis structure, and the Lewis structure for water. Water here is going to act as a Lewis base. It's got a nice pair of electrons here, a lone pair. And it's going to attach to the carbon here. But that carbon does not have an empty orbital. It has an octet of electrons. So what's going to happen? One pair of electrons from this double bond is going to move over to the oxygen, giving the oxygen a single bond and 3 lone pairs, which is an octet. What's left then is a single bond. And so before we put this on here, the carbon has, well, let's do it this way maybe. The carbon here does not have an octet because that electron moved, the electrons moved. So now this one can accept electrons, and the oxygen can donate electrons. So these hydrogens get donated, these electrons get donated to that hydrogen, and these electrons go to be a lone pair on that oxygen, and we end up with carbonic acid. And I saw some eyes that went, yeah, yes.
So this definition of acids and bases, is this trying to like expand, it's obviously trying to expand like what it means to be an acid or a base, but was this like because they noticed something was happening, something was corrosive that they didn't expect to be corrosive, and they were trying to figure out why?
That's an excellent question. Why did they come up with the definition of Lewis acids and bases? Off the top of my head, I have no idea. It's an excellent question. I think they did observe this behavior of donating electron pairs and recognize that as being very similar to the donation of hydrogen ions or protons. And it can be included in that. That's my guess. I don't know. It's an excellent question. Anybody else? No? Okay. Question of the day. So cations can also act as Lewis acids. Now, remember we said that small, highly charged cations can be acidic, right, from a salt solution. So here is a little more information about how that happens. I need to erase part of aluminum there. So aluminum with a 3+ charge has empty orbitals, right? And here we've got 6 water molecules, and they each have 2 pairs of lone pairs, right? 2 lone pairs. They have a pair of lone pairs, whatever. They have lone pairs. So each water molecule can donate a lone pair to aluminum, forming a coordinate covalent bond, and we end up with this adduct, which happens to be a complex ion. Any questions? It's all about accepting electrons.